Good morning. Today we have our last class and we'll continue reviewing for the exam. Just to remind you, the exam is right here on Monday morning, 8 o'clock. We'll start. Try to be on time so that you have your full time, although I'm not sure you'll need complete 3 hours, but you have 3 hours if you need it. So in general, are there any questions about the exam before we continue on with the practice exams that anybody wanted to ask? Yes?
So how's the grade breakup going to be between comprehensive and exam 3?
Well, it's whatever was in the syllabus. And as I recall, the exam 3 was more heavily weighted than the comprehensive part by quite a bit, like 2 or 3 times as heavily weighted. I thought each exam was like 25% of the grade or maybe 30% of the grade, but it's whatever's in the syllabus will tell you exactly how that breakdown goes. But if you find that you simply don't have time to do both, I would suggest spending more time on exam 3 over the last 3 chapters because that's the one that's going to come in most. Okay, other questions in general? Alrighty, then in that case, we will continue with the exam, practice exam 3B, and we had completed problem 5, and I want to begin on problem 6. Problem 6 is one of the questions about electrical stimulation of nerves. And the idea is that if you have an extracellular potential produced by some electrode or something, it's going to create what's known as the activating function, which will excite the nerve. So in this case, I'm going to give you what the extracellular potential is. In class, we did a case where we said it's a point source of current, and we figured out what the extracellular potential is. But let's assume that the extracellular potential is going to be some constant V0, another constant A squared over X squared plus A squared, where X is the distance along the axon. Now, what you're going to do, first of all, you're asked to simply plot the potential versus X for a negative value of V0. So in this is like just an almost middle school type of a thing. You just ask to plot what this function looks like. So at X equals to 0, A squared over A squared is 1, you just get V0, which happens to be a negative number. So it's down here. As X goes to infinity, the denominator gets huge, so it goes to 0. And what happens if X is equal to A? If X is equal to A, you get A squared over 2A squared. So at A is just down to a half. So the function looks like this. It's an even function. And this is VE of X versus X. So there you have it. So it's largest right here at the center and falls off. Then, part B, you're asked to calculate the activating function. And as promised, you don't have to remember what the activating function is. The activating function is given as B squared VE dx squared times the lambda squared. Sometimes it's included, sometimes it's not. So you want to plot the activating function and you want to calculate it. So you got 2 choices. If you could just calculate the activating function and then plot your calculated function, or you could just say, well, what's the second derivative of this? So let's do that first, just to show that you don't really have to calculate the thing out. Second derivative is the amount of curvature. So this thing here looks kind of like a parabola with a curvature up, so it's going to be a positive curvature. Over here, it's sort of like a parabola with curvature down, but it's changing more slowly. So then over here, somewhere in the middle is the transition or the inflection point. So it's going to go to 0. It's going to look something like this. You get that just by doing the derivative in your head. Or, as I said, you can do the calculation. If you want to calculate the activating function, you got to take 2 derivatives. Let's start by taking 1. We just use total derivatives because it's a one-dimensional problem. What's the derivative of this thing? Who can help me out here? It's got a V naught and a squared, those are just constants. So we'll drag those out. 1 over x squared plus a squared. That's the same as x squared plus a squared to the minus 1 power. Derivative minus 1 times x squared plus a squared to the minus 2, which would be like this. Squared, and then the chain rule times the derivative of the stuff inside the parentheses, which is 2x, excuse me. That's the first derivative. The second derivative is harder because now you got a product rule. What's the product rule say? Here you have
one term times the derivative of the other, second term times the derivative of the first term.
Okay, so here we're going to take the derivative of the first term. We'll write this as minus 2x, the first thing, times x squared plus a squared to the minus 2, the second. So the derivative of minus 2x is just minus 2, and that's x squared plus a squared, so we'll write it to the minus 2. And then you have the first function times the second, so minus 2x, and now we have to take the derivative of this, which is this to the minus 2, so you have minus 2 times x squared plus a squared to the minus 3 times the chain rule 2x. All right, so we're almost there. We can simplify this because this looks like a big mess right now. Well, everything has a 2. There's a 2 and there's a 2, so we'll take those out. 2 v naught a squared. And I'm going to factor out x squared plus a squared to the 3 downstairs. And what I'm left with is, I took out that 2, there's a minus. This had x squared plus a squared to the minus 2. When I factored out the minus 3, I'm left with x squared plus a squared upstairs. So I get a minus x squared minus a squared. That's the minus 1. We already took out the 2. And then there's a minus and a minus becomes a plus. That 2 we factored out, but that 2 and that 2 are still in there. So 4x squared, and this thing we factored out. So it becomes, let me just make sure I'm on the right track. Yes. 4x squared minus x squared. So 2 v naught a squared x squared plus a squared to the 3, and times 4 minus 1 is 3x squared minus a squared. And there you have it. At least the second derivative. You can multiply it by lambda squared if you want. That's the activating function. At least the second derivative. And if you plot that, well, it's essentially this behavior. You find that it's 0 at x equals 1 over square root of 3, so it does have that 0 there and there. It's largest at x equals to 0. You might say, oh, it's negative at x equals to 0, but remember v0 is taking as a negative value in this case, so it is positive up here. And it dips negative when your x is big enough that this term dominates. The whole thing's positive except v0 is a negative number, so it goes down and it's negative. All right, so that's the activating function. Remember, the activating function is what tends to stimulate the nerve axon to be excited. Now, probably the most important part of this problem is the last part, where it says, assume the transmemory potential, Vm, is equal to the activating function. Now, that was the case when a couple of terms in the cable equation were small, so this is just going to give you where Vm is big. Okay, then an excitation occurs where Vm reaches some threshold value. Find the ratio of the stimulus strength required for anodal and cathodal excitation. Well, this is cathodal. And you can calculate what you have to reach some threshold value, so V threshold has to equal basically this thing, times lambda squared, because that's in the activating function. Has to equal lambda squared, and where, this is for the cathode case. The cathode case, where is the largest value of the activating function? 0. X equals 0. That's where this is peak. So you evaluate this thing at x equals 0. 2v0a squared over a to the 6 times minus a squared. So you'd end up getting minus 2 lambda squared v naught over a squared. And you can figure out this is actually the threshold. It's this thing that should be the for the cathode case. So V cathode is minus V threshold a squared over 2 lambda squared. Okay, that's what it takes to stimulate with a cathode. So, what if you want to stimulate with the anode? That means flipping the sign of the stimulus. If you flip the sign of the stimulus, this picture comes backwards. This is hyperpolarization here, and you're relying on your stimulus out here to be your depolarization to excite the axon. And because this is a smaller peak, you have to turn your stimulator up. So what you have to do is you have to figure out how big is the activating function right here. How do you do that? Anybody remember what we did in class? How big was that activating function? Well, you gotta figure out where its peak is at. To figure out where its peak is at, you gotta find where its zero derivative. So you plug that value of x in and get the peak. So you gotta take a third derivative of this thing and set that equal to 0. I want to make sure we get through all these practice exams today. So I'm going to leave that as an exercise for you guys to do. Let's see. But if you do that, you will find that the peak occurs at x equals to a. Almost by magic. It's just that simple. But then you put in x equals to a into the activating function, and you get that the threshold has to equal to lambda squared times the activating function evaluated at x equals to a. This is 2v naught a squared. And now this is a squared plus a squared, quantity cubed. So it becomes, what, 2 to the third, or 8 a to the 6 times x is equal to a. You get 3a squared minus a squared, or 2a squared, which is equal to, so if you solve this for v naught, which is now the anodal case, because this is for the anode, you're going to get, oh gosh, there's going to be a 2 here, and a 2 here, and an 8 there, so you're going to get, okay, it seems a little odd. What's happening here? It's equal to pi divided by capital stimulus to peak. This is the same as in my notes. Why am I getting this different? 2v naught. I get 2 times. Okay. If you had x equals to a squared to a squared, that's going to be 2a squared. 2 raised to the cube is 8. And if you have a squared, you get 3 minus 1 should be 2a squared. Okay. So that 2, and that 2, and there's an 8, so that's a 4. That should be a 2 down here. It's downstairs. So it's downstairs. So this here. This becomes 2, but it's upstairs. That's where I was getting in trouble. 2 into 2 into 4. They'll cancel, give you a 2 downstairs, but you're solving it for VA, it becomes up to upstairs. And this would be a squared, so a squared over 2 over lambda squared, which is equal to 4 times v threshold a squared over 2 lambda squared. Now why do I do that? Why did I do it like with the 4 out front? Because this is exactly the same as that. So if I want the ratio of anode to cathode, it's just going to be 4. So really the answer is 4. If I turn the stimulus to opposite polarity, so now I've got to stimulate on this little peak instead of the big peak, I've got to turn the stimulus knob up by a factor of 4. And that's the idea for the calculation. So, this is an example of extracellular stimulation. We looked at this. We looked at ways you would stimulate. If you stimulate cathodally, you stimulate here. And if you stimulate anodally, you'll stimulate off to one side. And then we used that idea to talk about other things you can do. We talked about how if you had an asymmetric case, you could make yourself into a situation where you're stimulating here, not stimulating here, but stimulating on this side and bump in and get blocked by the hyperpolarization, and you've got a one-way stimulator. And we talked about ways you can use that in neural stimulation. So that was example problem 6. And it was a little bit long-winded. You're going to need to be comfortable doing kind of some simple derivatives. You won't need to be knowing how to integrate much, but you need to know how to differentiate. Any questions on that? That's the activating function. Okay. Problem 7. We're not going to do this in detail, but it's one of these cases with the hexagons. I've drawn over here on the board the hexagons. And the only difference between this example and what we did in class is instead of having 3 states, excited, refractory, and quiescent, we have 4 states. Excited, refractory 1, refractory 2, and quiescent, which is kind of like cardiac tissue. Goes up, excites, and then it sits there refractory for a long time. So it makes sense to give it a couple time steps, and then it'll finally return back to rest. And the idea is you start with excitation all along this edge here at time 0, and then you let it go up for a certain amount of time. The problem tells you how long. So after a few time steps, what does it look like? It looks like excited states here, and with the first refractory behind it, and the second refractory behind that. And then in this problem, it says, okay, you get to this point, and then we're going to stimulate from this side. And we're going to basically make all of these states excited. And this is going to overcome whatever was there before, and it's going to excite all these states like this. Okay, now, this would actually be a little clearer if I put in another row. Let's put it just down here, because that's where we'll need it. Okay. What happens? Are there any phase singularities? Well, last time we said a phase singularity is where excited, quiescent, and refractory meet. In this case, it's where quiescent, excited, and either one of the refractories meet. And that's going to be one spot, and I guess this is all E's here, because we're exciting this whole side. You get one spot, it's right there. So there's the phase singularity. Now, what happens? Do you get excitation that's going to be going clockwise? You can get a spiral wave. Does it go clockwise or counterclockwise?
Clockwise.
Counter. It's going to, next time step, this is going to become excited. This one's going to go back to quiescent. So then it's going to go up here. And so on. It's going to start a counterclockwise single spiral wave because there's only one. There's no other places where you could have refractory states. I mean, this has E, R1, and R2, but we said it has to be E, quiescent, and one of the refractories. Now, if you do this in detail, which you may want to do, but we're not going to take time to do, you're going to find that this phase singularity actually moves a little bit. It moves from here over to here and back. So if you watch this over several time steps, the phase singularity does what's called meandering. So it's a little bit different than what we did in class. In class, you found that phase singularity was rock solid and just sat there. In this case, it meanders around in a real simple pattern, just back and forth, back and forth. Also, yes?
So would that be considered two singularities or just?
It'd be considered one phase singularity that meanders around. Because if you look at any snapshot like this one, you see only one phase singularity. The only reason you know that it moves around is because you look at a bunch of snapshots and put them together in like a movie, and then you see it moving around like that. But it would be considered just one phase singularity. And the other thing is, if you did this and you looked at it over time and you asked then, how often does this repeat itself? What's the period of the spiral wave? You'd find in this case it's got a period 4. It's got a period 4, and it's not entirely obvious, but the meandering ends up adjusting things so it has to go through all 4 states before it can go back to where it was. So it's a period 4 spiral wave, single phase singularity. So that's the case. So there's no calculations that have to be done with that. I mean, you might want to bring colored pencils to the exam if you think it would help you. I'm not going to be grading on neatness, but I would certainly give you the hexagon pictures like I did in class if this was on the exam. Okay. Final question for this one is the essay question. Describe chaos. How is chaos different than a purely random behavior? What is meant by sensitivity to initial conditions? What is the butterfly effect? So, what is chaos? Rebecca, what do you think chaos is?
I think it's like the second part where it's different than random numbers.
Okay.
Because it still follows the equation, but it gives you seemingly random numbers.
Yes, so it's a deterministic equation. Is there a way that you could see that if you plotted them in some special way? Yeah, oftentimes if you plot, you're going through it step by step, updating the numbers. If you plot the old one versus the new one, you'll often see the mapping that is involved has come out in that plot. Where if you just plotted it as a function of time, they look like they're random numbers. But if you plot it in a special way, what's called phase diagram, it works. Now, what is this bit about sensitivity to initial conditions? Yeah.
The sensitivity to the initial conditions is basically what causes the butterfly effect in it. If you have one set of initial conditions, the graph could look one way, but if you were to start just slightly further forward in that graph and use that as the initial condition, it could come out as a completely different graph.
That's right. That's right. So one way to kind of see this is one system that gives you chaos is a rotating nonlinear pendulum. And it's a pendulum not that swings like this, but can go all the way around and turn around. And this pendulum, if your initial conditions are the same, it'll always repeat itself. If they're slightly different, it'll look about the same as it was, except sometimes it'll come up and not quite make it over and swing back. And for a slightly different condition, it'll come up and just make it over and swing around. And now it's completely different. The dynamics of those two cases for the rest of the time will just be completely diverged. That's an example of how you can get this sensitivity to initial conditions. It's often compared to making taffy, where you stretch and then you refold it, and then you stretch and then you refold it, and all this stretching and then refolding can mix things up, even though the process is very deterministic. Stretch, fold, stretch, fold. So that's a little bit about chaos. You'll have one essay question on both the exam 3, and there will also be one of the previous essay questions showing up on the comprehensive part. Okay, so we're ready to do exam 3C. I'm going to erase the board, and while I'm erasing the board, do you think whether you have any general questions that you want to make sure get asked? Because that's highest priority. Yes.
So the question, the essay on the comprehensive, that's going to be an exact one that you use?
Exactly. I made it up, and what I did is I went and I cut and I paste. The only difference will be the problem number because they may be numbered differently, but the exam, the questions will be exactly the same. Even numbers, if there's numbers involved, will be exactly the same. So literally, it pays just to study. I mean, you could take a first grader and tell them memorize this, and if they work hard, they ought to be able to memorize the solutions to those problems.
Oh, sorry. So all the problems on the comprehensive will have been on past tests.
On past tests or practice tests. So that means there's quite a few of them. And you should have the solutions to those already. So I don't recommend just purely memorizing them. It'd be nice if you knew, but you can at least do both. And I want a little bit of it to reward hard work, as well as most of the class rewarding your actual knowledge and your ability on the exams. Other questions? Okay, then practice exam 3C. In the bubble experiment described in class. So the bubble experiment was, we had a nerve axon and we put a toroid around it in order to detect the magnetic field. And then during the experiment, so the whole thing's immersed in a saline solution. Bubble got caught between the nerve axon and the inside of the toroid. So the question is, did the measured magnetic field get larger, smaller, or stayed the same? The good news is there's only 3 choices. Well, it's actually a little non-intuitive because you might think smaller, but in fact, what happens is you're measuring the magnetic field, and that's caused by current going down the axon plus some of the return current that comes back. And that, since it's coming the other direction, sort of cancels out some of the current. So the net magnetic field is the total current going through the toroid, which is this plus some of this. If you block the stuff coming back, you actually have a bigger magnetic field because you have more net current going through the toroid. It's very important that the return current is kind of going the opposite direction as the intracellular current. So let me see if I can draw a quick picture here. You get a toroid here, and here's the nerve going through it. And normally you got a current coming down here and some of the current going back through while some of it goes around. This current, the return current, partially cancels the intracellular current. The magnetic field, which is the net current, is smaller. And if you block that by a bubble, now you just have intracellular current. You don't have any cancellation from the return current. You got a bigger signal. Okay. What's the name of the part of the heart that electrically connects the atria and the ventricles? Yeah. That's the AV node. So you want to be particularly knowledgeable about the conduction system, the SA node, the AV node, and a little bit lesser important, the bundle of His and then the Purkinje fibers which spread the signal. Okay, so there can be a electrocardiogram. There's nothing there except an electrocardiogram. I know it's a little hard to see from where you're sitting, but you got to identify it. The electrocardiogram looks something like this. What's that? Literally, what's that? It's fibrillation and ventricular fibrillation in particular. If you had some QRSs on top of this, you might say atrial fibrillation. But the fact that all you have is just a random noisy signal means it's VF, or ventricular fibrillation, which is the one that's fatal in 10 minutes. Okay, what is the name of the main vessel by which blood leaves the left ventricle and goes to the rest of the body? What's the name of that vessel? You only know one vessel in the body, that's the one to know. It comes out of the left ventricle and actually kind of goes in a little arch, and then has a big vessel which goes down and the rest of the body, but there's also a branch that goes up to the head. Anybody? Yeah.
Aorta.
Yeah, aorta. Yes, it's the aorta is the large vessel that comes out. It's the biggest artery. All the blood goes through the aorta, and then it branches out. It's a big thing. I mean, it's at least as big as your thumb around, and probably larger than that. And if you ever have a problem, if the aorta ever bursts, it gets an aneurysm or something, it's usually immediately fatal because it's all the blood's coming through there, so it's a disaster. Okay, those were the short answers, all or none. Let's do now problem 5, which is a feedback system. It's a feedback system that the book talked a little bit about, but we haven't really looked at in this class. And that is how the pupil of your eye changes with the amount of light. So, what happens? First of all, if your pupil gets bigger, given the intensity of light, the pupil grows, there's more light hitting the back of your eye. So, you have one part of the feedback system is, unfortunately, I use funny variables here. So, the area is going to be y, and the x is the light hitting a retina. That's the amount of light that hits the retina. If you're given I is just the amount of light coming in and hitting your eye. So that means if you make your area bigger, you make y bigger, you're going to get, well, I is just the amount of energy per unit area, intensity, times the area gives you the amount of light hitting the back of the retina. Now here's the feedback system. Feedback system is your body adjusts the size of your pupil so that, depending on how much light hits the retina. So if you start getting a lot of light hitting the retina, your body will shrink down the pupil. So this feedback relationship is basically saying your area is going to go, in our case, some constant over x. It's inversely proportional. So what we're going to do now is we're going to try to analyze this feedback system. First, we're going to draw it. To draw it just means you're going to, first of all, plot x versus y, and that's just going to be a straight line with some slope. And that says, remember, that says if you tell me what the light hitting the retina, if you tell me the area, I'll tell you how much light hits the retina. And then, so that tells you what your x is. And then the feedback says, if you tell me how much light is hitting the retina, I'll tell you how big the retina is going to be. And that is 1 over x, so it looks like that. So right now we don't have any numbers to put on the plot. But this tells you what y is, and then it goes around and feeds back into here. So they both have to be true. All right, so now, that's the block diagram. Then you want to calculate this operating point for a given light intensity, I. So I is like a parameter. Given I, and K is also a parameter, it tells you how this feedback system is working. Perhaps if you, I don't know, drunk some alcohol or something, it might vary K. So both of the parameters could, in theory, vary. How do you find the operating point? So what would you find the steady state? This is a steady state case. How would you find the operating point?
You can do guess or check, or plug one into the other.
Yeah, I guess a check would be okay, except if we had numbers for these, but you'd have to guess. You could still do guess or check. But the easiest thing to do in this case is to just plug this y into here. Get x is equal to I times y, which is k over x, and then solve it. X squared equals ik. X is equal to the square root of ik. No. And once you get one of these, you can then put it into the other equation. Y is equal to k over x, which is ik square root, which is, you just put this inside the square root, it becomes k squared, cancels one of those, k over I square root. So now you know that the operating point is x equals ik square root, y equals k over I square root. And unless I give you numbers for I and K, this is the best that you're going to be able to do. All right. That was part B. Now, some of these problems, as you may guess, have multiple parts. Suppose you doubled the amount of light. Somebody came in and they turned the lights up in the room. So now it's a lot brighter. How is the system going to change if there's no feedback? And then we're going to calculate what happens if there is feedback. So for the moment, you have some disease or you've taken some drug that kills off this feedback system. If you double I, what's the new operating point with no feedback? Well, if there's no feedback, then this Y, which is really the result of the feedback, stays the same. So Y is going to be equal to K over whatever you had for the original I. But X is going to be now, it's going to have twice because now X is, we have a 2I there. So this would be the original I. And now X, the X equation is really 2I over Y. So you get twice that. So you would have, it's as if I became 2I in the X equation, so you get square root of 2 times your original I, K. So what you have is, why am I, it's not looking right. Okay, for there's no feedback. So that's the same IK on my answer sheet. I have, I've done this wrong. What I do is I say, Y didn't change, so my X now is 2I, which is 2I times Y, which is K over I square root, which is going to be, put it inside there, 2KI square root there. So, the light hitting the retina doubles, but your area doesn't change because there is no feedback right now because you took some drug. So now the drug wears off and your feedback system works. So now you double the light. What happens? Well, now you basically have X is equal to 2IY, and you have Y is equal to K over X. And now you have to solve them again for your system. And this is exactly the same solution as before, except there's a 2 in front of the I. So you get that K is equal to 2IK, and Y is equal to K over 2I square root. So this is with feedback. And what you find is that X looks the same as it originally did, except it's multiplied by square root of 2 times IK square root. So, with no feedback, X doubled. The amount of light hitting the retina doubled. With feedback, it only went up by 1 square root of 2, which is like 1.4. So you've sort of dramatically reduced the amount of light hitting the retina by doing this feedback system. So that's really the goal of the feedback system, is you want to keep the amount of light hitting the retina somewhat constant. At least you don't want to have a huge dynamic range. Your cones and rods in your retina can't respond to a huge dynamic range. So you want to try to keep those changes smaller, and you do that successfully with the feedback. Feedback problems. We talked a lot about those for the last few days in class. You want to be familiar with those. You want to be able to draw a simple diagram. If I give you numbers, it would be nice to make this quantitative. It's not absolutely essential, but you want to make sure at least it's qualitatively correct. And you want to be able to, you might if you had, instead of just this time independent case, you could have a case where one of these had a time constant. You might be asked to evaluate the time constant. You might be asked to evaluate the open loop gain. There's various things you can do on feedback problems. You've seen a lot of them in the homework, which you've just handed in. And this is one of those things that was talked about in class, was on the homework, and was on the practice exam. So any time you have something with all three of those conditions, it's fair game for the final. Yes?
Can you do open loop gain?
Okay. Open loop gain in this case. Let's just do the original case here. If I asked you for the open loop gain, I would want, first of all, the slope of this line, which is dx dy for this first equation. The equation that gives you x, you find the x dy equals to I. And then you want to find the slope of this one. And this is going to be dy dx, which is going to be equal to, it's a little harder, x to the minus 1, you get minus k over x squared. So the open loop gain would be the product of those two, minus ki over x squared. But you evaluate this at the set point. And the set point for originally was I times k square root. So the set point was minus ki over x squared, which would be ik minus 1. Looks like the open loop gain comes out to be minus 1 in this case, which is negative, so it's negative feedback. It's not a particularly large gain. And interestingly, it seems to be independent of the, if I've done this right, it's independent of the set point, which seems odd to me. I guess the set point, I mean, this slope varies, but somehow the set point adjusts so that it's always reaching up to a point at the same slope, apparently. So that's in general how you do the open loop gain. You find the slope of one of the curves, slope of the other curve, you multiply them together, and you put them on the, evaluated at the set point, and you get the open loop gain. Can't really do a time constant example here because this didn't have time in it. And generally the time constants get faster by 1 over 1 minus the open loop gain. This is what the factor that often comes in. But you can calculate it in first principles. Okay, so feedback. Lots of feedback problems are fairly easy to make. Okay, we got 2 more problems, but any questions? About 10 minutes for each problem. I should do the last 2 are a little long-winded. Okay, I'm going to erase all this, and we will do problem number 6. Okay, problem number 6 is calculating extracellular potential for an axon. So you have an axon that has a current which is I0 between 0 and B, so this is the x direction, and it has a current going the other direction, so it's minus I0 from minus B to 0. Everywhere else is 0. And you're asked to find extracellular potential out here at some point x, y. So first thing you have to do is figure out where current's going in and out. Current's coming out of the cell right here, a total amount I0, and it's coming out of the cell here. So 2 point sources. Here, current at double the amount has to be going in, so that's a sink. So 2 point sources and a double size sink right there. And the potential, which if this had been on the exam, I would have reminded you that the extracellular potential is I over 4 pi sigma r. I see I didn't actually say it on this practice exam, but I'm not expecting you to know all these equations. Which reminds me, if there's a question on the exam, he told us that there was no didn't have to memorize an equation, but there I need to know one, you can always come up and ask me. If I think it's something so fundamental that it's really a definition or just a math property, like taking the derivative of the sine function, I may not tell you. But if it's like this, where I forgot to give you the equation, I will give it to you. VE is equal to the current divided by 4 pi sigma, and the only thing that's hard is the R's. So here's current comes out, so that's the first one we have to get. So this spot here, from 0 to this point is x. This point, what we're really trying to find, this is b, and we're trying to find this distance and that distance. This one is y. What's that side? That would be x minus b. X minus b is this side squared, and this side's y squared, and square root, that's Pythagorean's theorem, that gives you the distance. And it's 1 over that because you took the I0 out, so it's I0 coming out. How about this term? What are you going to get for the extracellular potential with that? Somebody help me out here. It is now this value of R. First of all, it's twice as much current because you got 2. So you get 2 upstairs. And second of all, it's going into the cell, so it flips the sign, so it's a minus. How long is this R? Well, the bottom is just x. And the top is y, it's just x squared plus y squared square root. And the final one is way out there at minus b, and it's again plus and again a 1. But now it's going to be x plus b squared plus y squared square root. So you can get it. That's the extracellular potential, and that's pretty much what you can do. You're asked to plot it for a small value of y. Well, this is hard to plot real nicely unless you really do a lot of calculations. But y is small. If y is small, then this thing's going to get really big wherever the other variable in here gets small. So it's going to be really big and positive at x equals to b. It's going to be really big, but twice as negative when x is equal to 0. And it's going to be really big and positive when x equals minus b. And it's going to look something like this. So it's just going to have that sort of shape to it. I won't be too worried about the exact shape. Now, the next thing comes sort of a long-winded analysis, but the good news is it is kind of steps. You should lead you through it step by step. Factor 1 over y out of the bracket. Okay, I can do that. I naught over 4 pi sigma and the y. So if I factor 1 over y out, this y comes out. So it's going to be 1. I'll put that term first. And then this term doesn't have a y, so it's going to become x minus b squared over y squared. This one's going to be minus 2. The y came out, so I'll get 1 for that term plus x squared over y squared. And the nice thing is, this y we're going to eventually find is big, so those will be small terms. Plus 1 over 1 plus x plus b squared over y squared square root. Then I say use a Taylor series, and I give you what the Taylor series is. Put it up here. 1 over 1 plus z square root is approximately 1 minus z over 2. So, for large values of y, this is going to be x over y squared. X squared over y squared is basically going to be small. So it's always going to look like this for small z. So let's just use this Taylor series. It becomes 1 minus z over 2 is 1/2 x minus b squared over y squared. This one has a minus outside, and it's got a 2 in front, so it's going to be 2 plus x squared over y squared. And then this one's going to be plus 1 minus 1/2 x plus b squared over y squared. The 1/2 disappeared because it had the 2 out in front of it. Then you have to find that that and that cancel that. And then you have to multiply out these things. And it's a little bit of math, which I'm going to skip all the details of. But what you end up getting, so I'll put dot, 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 is minus I0 b squared over 4 pi sigma y cubed. Now the interesting thing about this is that the potential falls off as y cubed, the distance cubed. We didn't really talk about this, but if it falls off as 1 over r or 1 over y, it's a monopole. A dipole falls off as distance squared. It's a quadrupole source that falls off as distance cubed. So you basically have 2 dipoles that are oppositely oriented. A dipole pointing that way, a dipole pointing that way. So the net dipole moment's 0, but there is a quadrupole moment for a nerve axon that gives you the potential. I wouldn't ask you about quadrupoles on the actual exam, but on the practice exam, sometimes I run out of stuff and I throw it on. So, we talked about extracellular potentials and the dipole approximation. It wasn't quite something we stressed as much, but you ought to be able to follow through, especially if you're kind of led through the problem. Questions on that? That one's a little more advanced than you'll probably see on the exam, but you could easily see a case, at least this first part, where you're asked to calculate the extracellular potential given the situation with the axon. That's certainly fair game. We did that on multiple times. Okay, problem 7. Problem 7 is similar to the problem we just did on activating function, but it's related to magnetic stimulation of the nerve. So, what you have is you have an electric field along the nerve, and it comes from magnetic stimulation. And remember, the activating function is the first derivative of the electric field. Second derivative of the potential, first derivative of the electric field. So I tell you the electric field is equal to, it's one of these funny things, x to the 4th minus 2x plus 1, so minus 1 is less than x is less than 1, and 0 otherwise. Alright, so you need to plot this. Ex versus x. And we'll say this is 1, this is minus 1. So it could easily be a lot of these plots on the final. You need to be comfortable plotting things. Okay, so let's plot it. Well, first of all, if you're outside the range minus 1 to 1, it's 0. So let's immediately go like this. If you're at x equals to 0, those two terms go away, you just get c, so you know it's going to be up here at c. So the question is, what does this look like in the range between, how does it connect from c is 1, c down to 0? Well, a couple things you could do. First of all, if x is 1, you get 1 minus 2 plus 1. So it goes down to 0. It's a continuous function. That's good news. If this was not continuous, this would be sort of a pathological problem. What does it look like? Well, you guys are looking probably odd at this, because this is actually x squared. It is an even function. There. Okay, that's what it looks like. If you looked at this, it's not a parabola. That would be if it was x squared minus 2x plus 1. It actually has sort of a sigmoidal shape like that. is approximately what it looks like. You can plug some numbers into your calculator, which you should bring, and to figure out. You know it's an even function, so just try a few numbers here and then draw a smooth curve between them. Or you could note that this looks like x squared minus 1 squared, which actually it is, and that might even make it easier. That's a parabola that's been squared. Okay. So that is the electric field as a function of x. The activating function, again, I give it to you as minus dEx dx. What's that going to be? Well, minus, that's x to the fourth, so it's 4x cubed. The minus will cancel that minus, plus 4x. That term won't give you anything. So you'll get minus 4 times x cubed minus x. Or in other words, minus 4x, x squared minus 1. Well, this is kind of good. I sort of spent some time figuring out what function I wanted. This has, at x equals 1, it goes down to 0. So the activating function also goes down to 0. But now the activating function, minus 1, is going to be, first of all, it's odd now. And it's going to have to be 0 out in this area, because it was 0 and the derivative was 0 is 0. Here, it's going to be, well, it's going to go up as x, but it's got a minus sign in front of it, so it's going to look something like this. It's going to be a parabola, and a parabola, but not quite a parabola shape, a parabola times x. So it probably has something a little more like that. Something like that is going to be the shape of the ex dx. And you can plug numbers into your calculator and get the exact shape. I think there's a c floating around in front of all this that I forgot to bring down, but technically there should have been c, factor of c in front of all that, which I forgot to put in. Okay, now here's the key part. Suppose you use this for an experiment. You stimulate with your magnetic stimulator. Where are you going to excite? You're going to excite where the activating function is biggest. So you're going to excite right here. Then you flip the polarity, and where are you going to excite? When you flip the polarity, now this is positive, so you stimulate here. Now suppose I was measuring, I did the stimulation up here, and I was measuring the arrival time of the action potential down at my thumb. So I had an electrode here, and I had it hooked to an oscilloscope. You're going to stimulate at two different spots. One time it's going to take a shorter time to get there. One time it's going to take longer because it's got longer distance to travel. It's got this much longer distance to travel. So suppose I asked you, what is the delay between the time difference between the arrival of the two action potentials as I flip the polarity? Okay, well, it's going to be, let's see, delta over the time difference is going to be the speed. I'll call that u. So t is going to be delta over u. And u's given in the problem. So what I got to do is I got to find out what delta is. How do I find out what delta is?
The derivative find the zeros.
I want it this. I'm saying it excites at its peak. Its peak is where the derivative is 0. So I've got to take this function, take its derivative, and set it to 0. Okay, I can not have to worry about the minus 4. I basically just have to do d dx of x. Let's multiply it out. Let's use it this version of it. X cubed minus x. I don't care about constants. I have to set that to 0. So that's going to be 3x squared minus 1 is equal to 0. X is equal to 1 over 3 square root. I put that in for the activating function. Well, actually, no, I don't have to do that. I got what x is. So that means this is plus 1 over square root of 3, and this is minus 1 over square root of 3. So delta is going to be equal to 2 times square root of 3. It's twice that. So the time is equal to 2 over square root of 3, and the problem says that these numbers are in centimeters, over the speed, and the problem says the speed was 35 meters per second. Now I gotta be a little careful here because this number was in centimeters, so it would be 3.5 centimeters per second. Which would, if you do the calculation, did I do that right? It would be meters per second. No, if it was 35 meters per second, it would be 0.35 centimeters per second. So then if you do the calculation, it comes out to a time shift of 0.33 milliseconds. Something seems odd here. Let me just make sure I'm doing this right. The speed is 35 meters per second is 3. The way I did it in my example is 3.5 centimeters per millisecond. Let me just do it this way. Meters per second times 100 centimeters per meter. So, I've screwed up terribly. That's going to be 3500 centimeters per second. So yeah, this is why I was getting confused. I did it the wrong direction. And this comes out. Now this is huge, so the time is small and it's less than a millisecond. Okay, so I screwed up, but there's a lesson there. I thought about my answer, and I said to myself, something looks like it's screwed up. So, one thing we've been stressing all semester is you look at your answer and you say, does it make sense? In that case, my answer didn't make sense because I had messed up, so I went back and I figured out why. Do that on the exam. Calculate something. If you get your time distant, your change, say you had this problem and you calculated your t and you came up with 3 hours, something went wrong. And you know that something went wrong, and you go back and you figure out why. I'm not going to give you any problem that's totally screwed up like that. Okay, finally, the essay question here. Describe the heart's conduction system. Name the parts and their functions, and explain what problems. So just briefly, since we're almost out of time. SA node, that's the pacemaker. If the SA node doesn't work, you might have a slow or a rapid heartbeat. AV node is the connection between the atrium and the ventricle. If it doesn't work, you got heart block. And then after that, this goes through the bundle of His and spreads through the Purkinje fibers and excites the whole inside of the ventricle and begins your QRS wavefront. So, those are the practice exams. I will send you the homework solution and the practice exams here in the next hour. That's what I plan to do right when I get back to class. And then I will see you on Monday, 8 o'clock. If you haven't handed in your last homework assignment, put it right up there on your way out. Any last questions? Good luck, and I'll see you Monday.